NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Thank you very much for coming out on this rather soggy evening and fighting the LA traffic. We're really grateful for your attendance, for sure. So let's jump right in, shall we? The Nuclear Spectroscopic Telescope Array, or NuSTAR, which launched in June of 2012, is the first telescope in orbit to focus X-ray light. Compared to the previous generation of non-focusing observatories working in this energy band, this change in technology provides NuSTAR with 10 times sharper images and 100 times improved sensitivity. High-energy X-ray light provides a unique probe of the most energetic phenomena in the universe, from flares on the surface of the sun, to the explosions of stars, to the extreme environments around neutron stars and black holes. This talk will present some of the recent highlights from the NuSTAR mission and describe how they are changing our picture of the extreme universe. Tonight's guest earned his AB in physics at Princeton in 1991 and went on to earn his PhD in astrophysics from UC Berkeley in 1999. He came straight from Berkeley to JPL, initially as a postdoc to work with Peter Eisenhart, but switched to the Spitzer Space Telescope science staff about 18 months later. Since then, he's worked on WISE, Euclid, WFIRST, a CubeSat, the Habitable Exoplanet Imaging Mission, and several other missions and mission concepts. But his main job currently is as the NuSTAR project scientist. Scientifically, his main interests are observational cosmology and extragalactic astrophysics. But he's had a sideline finding the most distant objects of various source classes, including the most distant object, like period, the most distant galaxy, the most distant radio galaxy, the most distant quasar, the most distant galaxy cluster, and the most distant supernova. He's also very interested in fields where infrared satellites and X-ray satellites make important contributions. Specifically, distant galaxy clusters and obscured black holes are both well served in observations in those two wavelengths. As one might expect, he's a very enthusiastic observer, having logged more than 500 nights at telescopes worldwide over the past 20 years. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Daniel Stern.
Thank you. Thank you for braving the weather and coming out for this. I'm excited to have the opportunity to talk to you about some recent highlights from the NuSTAR mission. Here is the artist's conception of NuSTAR, and I'll talk about spinning black holes, exploding stars, and hyperluminous pulsars. And I list a couple other missions that I'm involved in if people have questions afterwards about those. So diving in a little bit, so NuSTAR is the Nuclear Spectroscopic Telescope Array. Our little tagline is bringing the high-energy universe into focus. We were the, not quite right in that tagline. We're not the first to focus high X-ray light, period. We're the first to focus high-energy X-ray light, so the more energetic X-rays. And we have a change in technology that brought about a factor of 200 gain in sensitivity compared to what has flown before us. We're a NASA Small Explorer mission. That's a line of missions that costs about $150 million. It's about as small as NASA goes into space typically for in astrophysics. So about, more expensive than an indie film, less expensive than a blockbuster. And I think we've gotten good value out of it, giving it into the LA context. We launched in June 2012. We were initially designed for a 2-year mission, but everything's been going swimmingly, and we've been continued on for continued funding. And so now we're a couple years past that in this extended mission since August 2014. The principal investigator, or PI, is Fiona Harrison, who's a Caltech physics professor and actually now the chair of physics, math, and astronomy at Caltech. We were the first mission that NASA selected with a female PI, which is both very exciting and also kind of embarrassing because it was about 50 years into NASA's history before that had happened. Another mission selected after us actually launched before us with a female PI, so we weren't the first in orbit with a female PI. I'm the project scientist. I'm a JPL employee. I spent a lot of time at Caltech. And the NuSTAR mission has been a really fun project. It's about 150 scientists on the science team around the world. We have the Italian Space Agency have a big role in it. The Danish Technical University in Copenhagen had a big role. And then here's Columbia University, Berkeley, I guess. So it's been a fun ride with a nice, good team. I mentioned that we were a NASA small explorer. Just to explain to you in the astrophysics, so everything that NASA studies outside of our solar system counts as astrophysics. And the smaller line of that are these explorers. We have the mid-size explorers, and then small explorers, and then sometimes these mission of opportunities, which will often be NASA building an instrument on a foreign foreign telescope. And so there's NuSTAR, one of the more recent small explorers, and then I circled a couple other ones that came out of Pasadena that you might have heard of, WISE and GALEX and ACE. And so it's a really exciting line. It's had really exciting discoveries. And these missions are relatively small for NASA, so it's relatively small teams and relatively quick timelines from selection to launch. And in fact, by the end of this month, or maybe by the end of next month, the next SMECs will be selected. They do a multiple stage down select. So at this point, there's 3 missions competing for 1 slot. One of those 3 is called SphereX. It comes out of Caltech and JPL. So hopefully, maybe even next week, we'll find out that the next SMECs will be coming out of JPL as well, and you'll be able to hear a talk about that in a couple of years. Outline for the talks, I'll start off with a little bit of overview of what the NuSTAR mission is like, the engineering of it, the launch of it, and then I'll hit on those 3 science topics from the title of the talk. And here's the website, and here's the artist's conception of what NuSTAR looks like. We work in the high energy X-ray regime. So this is the same energy X-rays or energy light that doctors and dentists use to study your body, that airport security use to study your luggage. These are very penetrating light. They're able to go through material. We're not sending out X-rays and then studying X-ray images the way doctors do. Instead, we study some of the most energetic, powerful phenomena in the universe that create X-rays, like supernovae, the sun, black holes, and use that to understand the extreme universe. We work in the high energy or hard X-ray regime. I'll try not to use the term hard, but that's the technical term. We're the first mission to focus X-rays in this high energy X-ray regime. There have been several missions that have done similar things in the lower energy X-rays. I have a picture here of Europe's XMM Newton satellite. You might also have heard of NASA's flagship Chandra X-ray Observatory that works in a similar energy regime. Those missions launched about 15 years ago and are continuing and doing really exciting work in the lower energy X-rays. And we actually partner up a lot with those missions to get a full X-ray study of interesting objects. NuSTAR, I keep saying that we're focusing optics, so I'll describe that a little bit. We're the first focusing X-ray satellite in orbit. Previous generations of X-ray satellites use something called coated aperture optics, which are like a pinhole camera, or I like to think of it as kind of have like a LED screen with lots of holes in it, and then the satellite's slewing across the sky, just rotating around, and you watch how the shadow pattern changes, and you're able to figure out where the X-rays are coming from in the sky. And so that sort of design, this coated aperture optics, by nature gets you blurry images, you need really big detectors, you need this big LED shielding thing. And so it ends up being a very heavy satellite. I have a picture here of the European Integral satellite. NASA also has a coated aperture satellite up in orbit right now called the BAT Alert Telescope on the SWIFT satellite. Those sort of designs are pretty heavy, and if you're a NASA person, you know heavy means expensive. It costs a lot to launch things into space, so you try to make them as light as possible. NuSTAR instead does focusing optics, and X-ray focusing is a little bit tricky because if you had like your usual antennas like we see here, or like radio dishes you see, or normal optical telescopes, X-rays tend to like to go right into it and penetrate through. And so when you want to focus X-ray light, you have to do grazing incidence optics. So the X-rays come and you kind of nudge them, almost like a rock on a lake. And so our design is something called Ultra One optics. We have two bounces to the X-rays, and then it sends them down and focuses them on where we have our detectors. The optics end up, so rather than looking like a dish, it's a cylinder nudging the light in. And in fact, what we do is we have 133 shells, concentric shells, almost like Russian nesting dolls, that make up our optics. So our optics are about yay big. They weigh about 50 kilograms, and they focus the light in. Here's a picture from a Scientific American article about a year before we launched, a year and a half before we launched, where they took pictures of different parts of NuSTAR being built. And this shows you the top-end view of the optics. So you have these concentric shells, 133 of them, with little graphite spacers. This is a big effort to build this thing. And we built 3 of them. We launched 2 of them on the satellite. So this change in technology buys NuSTAR a huge gain. We're about 10 times, or even more than 10 times sharper images, about 200 times more sensitive images. And actually, because we weigh so much less than the other design, we're about a quarter of the cost of the integral satellite, for example. So it's just a game changer in high energy astrophysics. Here's an example showing you what that change buys you. Here's an optical image of a nearby galaxy, NGC 1365. It's a barred spiral galaxy. It's just the pretty picture is a ground-based optical image. And then what I'm showing you here is the beam size, or essentially the pixels, for some of the other high-energy satellites in orbit. So Integral has this big circle here. Swift's pixels are about the size of the full moon, roughly about 20 arc minutes versus 30 arc minutes. And then NuSTAR's beam size is about the size of Mars. And so we get much, much sharper images. We're able to, whereas Swift and Integral might have said NGC 1365 has a lot of high-energy X-rays coming out of it, with NuSTAR, you're actually able to map it. And so here's an example of another nearby galaxy, IC 342. Again, the background image is an optical image from the ground of this nearby spiral galaxy. The purple is the NuSTAR image of it. And we actually see 3 sources. You see 2 bright guys in the outskirt, and there's actually a little bit of high-energy X-ray light coming from the center of the galaxy. And so with Swift or with Integral, all the previous satellites just would have seen there's X-rays coming from this, and they would have known if it was 1 source, 3 sources, coming from the center, from the outskirts. So it's a total game changer in what you're able to do. A little bit on the technology that allowed it. So here's the optics I showed you. We have 2 of them, actually, just to get more collecting area. Just a fun little story. They sit in something called the trash can, or we called it the trash can before launch, until the guys who were building it said, "Can you stop calling it the trash can?" And yeah, so the optics are yay big. They focus the light down on these detectors. We have 2 sets of detectors, one for the optics. They're both pointing at the same patch of sky. The detectors, whereas your cell phones use a silicon detector to detect optical light, for high-energy X-rays, you have to do a little bit of change. It's cadmium zinc telluride detectors. These detectors were all built at Caltech by Fiona Harrison's group, which is one of the world leaders in these high-energy detectors. These were built specifically for NuSTAR. Both the detectors and the optics, we flew an earlier version of NuSTAR on a balloon called the High Energy Focusing Telescope, or HEFT, which was really a proof of technology that the detectors and the optics worked. It just flew for a couple of hours, a couple of days, was able to look at very bright objects, but showed to NASA that this worked, and then that allowed us to then propose and get accepted as a satellite mission and really be able to exploit this energy regime. And then finally, the third key part of the technology is that these focusing high-energy X-ray optics have very long focal length. You need a really large separation from essentially your lens and your film, or your lens and your detectors. For NuSTAR, this is 10 meters, 30 feet, or about the length of a school bus. Chandra and XMM, those flagship lower energy missions, had similar focal lengths for their telescopes, but they were billion-dollar class missions. They were able to launch on a big rocket, fully extended. For NuSTAR, we had to extend after launch because we had to go on a little cheap, less expensive launch vehicle. And so we had this extendable mast that was built in Goleta, California, pretty close to Santa Barbara, by a company that specializes in extendables in space. They have about more than 100 things, some in orbit, some on Mars, with 100% success rate. The design for the one on NuSTAR was based on something that launched about 20 years ago on the shuttle called the Shuttle Radar Topography Mission. And so it was a very similar design to that. And then here's just a sense of scale. Here's a picture towards the end of the integration and testing of NuSTAR. So there's the two optics modules. The mast is deployed in there, and there's a person, just to give you a sense of scale. So we're a little bit bigger than a person. Our launch was this interesting launch vehicle called the Pegasus launch vehicle. Here's a little video of it. This actually isn't our launch. We launched at night, and so this is just archival footage of a launch. But essentially, they use an L-1011, a Lockheed 1011 jumbo jet, as a first stage. Takes the rocket up to 30,000 feet, drops it for 5 seconds, it ignites, and then takes you up into space. And so this all happened in June. The airplane took off from the Kwajalein Atoll in the Marshall Islands. And since that point, NuSTAR has been orbiting the Earth basically over the equator every 90 minutes and taking data the whole time. I heard on NPR this morning they launched a Pegasus. They did another Pegasus this morning, if you had heard, with something called Cygnus studying hurricanes. But there's beautiful videos of that. I just was watching that. So we get into space. First thing you do is you deploy your solar panel just to stay power positive. Exercise it, you're able to move the spacecraft around. And then about a week after launch, we deployed this extendable mast so that we could start focusing the X-ray light. And so this is the artist's conception of what that looked like. There's our 2 optics modules. We have 2 detectors down here. And basically the launch and then this were the 2 really scariest parts of the mission. This took about 40 minutes, and just like the launch, it went perfectly. And so it was a very cute design, that very simple and very compact, and then it extends out by this 30 feet. And so I'll just let that finish. And so we're orbiting the Earth every 90 minutes, taking data. There's the 2 optics units. With this very successful launch and this great new technology, we've been doing a range of really game-changing observations. Talk about first black hole spin measurements. So first off, what's a black hole? I could give a whole 1-hour lecture on black holes, do more than that even. We're not going to do that today, but just real briefly, black holes are these sort of crazy things that, if I take this ball and I throw it up, it comes back down. If I throw it higher, it takes longer to come down. If I throw it really hard, it would go up into space and reach, escape velocity and go out into space and escape the gravitational pull of the Earth. So way back, actually, even back in the 1700s, Immanuel Kant kind of did a thought experiment that you can imagine if you had something that its escape speed was the speed of light, then not even light would be able to escape from it. And so Immanuel Kant actually kind of came up with the idea that black holes might exist. And there was many centuries later before physics started showing that, yeah, we do predict they might happen. And then actually the first black holes were found by a Caltech astronomer, Martin Schmidt, about 53 years ago using the Palomar telescope with 3C273. So these are incredibly odd objects in the universe, very heavy, very dense, and very fascinating objects. A couple of things that we know about black holes. We know that there's a big black hole in the center of every large galaxy, weighing millions to billions of times as much as the sun. We know that there are smaller black holes weighing a bit more than the sun, 10 or a couple tens of times as much as the sun, peppered throughout galaxies. There's thousands in our own galaxy, and we see them in nearby galaxies. So astronomers, like all astronomers, know black holes exist, and that there's different types. Oddly, we only know of one in this intermediate range between the small and the big, and that's a big issue that I'll talk about a little bit later. Highlighting some more Southern California astronomy, one of the best studies of the nearest big black hole to us comes out of Andrea Gez's group at UCLA, and they've been using, for the last 15, 20 years, very advanced techniques on the biggest ground-based telescopes to watch stars moving in the center of our galaxy. There's a couple dozen stars that they've now been tracking for 20 years, and they find that they're all orbiting around a single point. You can use just high school level physics to figure out how much that single point must weigh, and it's about 4 million times as much as the sun. It's very dim. You see it flaring every once in a while. And there's basically, physics tells you that the only thing that could be that heavy and that dense is a black hole. And so this is one of the best studied black holes, is that one in the center of our own galaxy. Over the last 15 years, we've come to appreciate that probably all big galaxies have something that weighs millions to billions of times as much as the sun at their center. And they, about 1/2 of 1% of the mass of a galaxy is in this central little black hole. Things that we don't know about black holes is there's really extreme physics happening right near the black hole. It's space and time is being torn apart, as you might have seen in the Interstellar movie. Whoops. The really strong magnetic fields, crazy high temperatures, creating X-rays, for instance. And so there's a lot of work going on trying to understand the detailed physics of what's going on near black holes. The cosmic history of how black holes form and grow over time is a big area of study right now. We see black holes weighing 1 billion times as much as the sun, less than 1 billion years after the Big Bang. And basically, theorists say that shouldn't exist. The models have a really hard time creating things that big, that quickly, and then the observers find them. And then the other thing is we think that black holes are really important in how galaxies form and evolve over time, and that's a big area of study right now. So where does NuSTAR come in? So black holes, at some level, are very simple things. They're really mathematically very pure. There's only 3 parameters that define a black hole. Its mass, its spin, and then its charge. But any astrophysical black hole should essentially have 0 charge. So we really kind of think of just 2 parameters, the mass and the spin. Masses we've been measuring for the last 20 years, like that study by Andrea Ghez. You watch things orbiting the black hole, you can figure out how big it is. The spin of the black hole has been harder to measure, and that's where NuSTAR came in. Being able to measure the spin tells you about the environment around the black hole, a little bit about how the black hole forms. But one of the big issues is before NuSTAR, there had been this long-standing debate in the high-energy X-ray community about if you could even measure how fast black holes are spinning. And if you went to a conference before NuSTAR launched, somebody would give a talk about, we measure the spin of this black hole to be blah, blah, blah. And then the next person would come up and say, you can't measure the spin of a black hole. Here's our model. It tells you, we can take that same data and tells you nothing about how fast the black hole is spinning. So you had these 2 warring camps at conferences, and then most of the community was just sitting on the fence, unsure. And the way the people who are thinking that they're measuring the spin of the black holes were doing it is that one of the strongest features that you see in the X-rays from a black hole is a strong emission line of iron. You get very hot iron very close to the black hole. And so it basically comes from the region closest to the black hole. And that region closest to the black hole will depend on how fast the black hole is spinning. If the black hole is spinning very, very fast, the disk of material around the black hole gets brought in very, very close to the black hole. And so this, the iron is moving at incredibly fast speeds. It's so close to the black hole that you have light bending going on. And the emission line, this iron line, gets really spread out and has this really extreme profile that's from light bending and relativistic effects. In the middle, I have a picture of a black hole that's not spinning. And then on the right, I have a picture of a black hole that's spinning in the opposite direction of the material around it. And in those cases, the inner region is farther from the black hole, and you get less extreme bending of the light up from this iron line. And so this is all from a Sky and Telescope article prior to the NuSTAR launch by a postdoc Laura Brenneman, who's actually part of the NuSTAR team at Harvard. So that was one idea of what's going on with how you're measuring the spin of black holes. Other people said that we can explain these weird shapes to the iron line by just putting a lot of gas and dust in front of the black hole, and you can get these weird shapes from that. So you kind of had this one model where you had the spinning black hole, and you have this weird shaped iron line, and then it predicts that at higher energies you get this bump. And then this other model says that it's just gas and dust in front of the black hole that's giving that weird shape that looks basically the same in the lower energy X-rays that you could study prior to NuSTAR with Chandra and XMM, but had very different prediction of what you would see in the higher energies, which were inaccessible before NuSTAR. And so one of our first observations was we went to NGC 1365, that barred spiral galaxy I showed early on. Here's the low energy X-ray data from the XMM satellite with the two different models. One is the shape of this feature over here is all due to the spin of the black hole, and you predict that at higher energies you should get this big bump. The other model says this weird shape is all from gas and dust, and you have a very different shape predicted in the NuSTAR band. So one of the early NuSTAR observations was this joint observation, and bang, the NuSTAR observation sat exactly on that model. And so at this point, almost everyone has dropped off the fence, has agreed that you are able to measure the spins of black holes. There's, I think, 2 people, maybe 3 people left in that camp are still fighting for that. But it seems very convincing, and there's been a range of studies from more than a dozen black holes all supporting this, and showing that we're really able to measure how fast the black holes are spinning, which tells you how close that material is coming to the black hole. And it's coming, just a few times the Schwarzschild radius away from the black hole. It's really extreme. And so just summarizing, and the other thing, pardon, is that with the NuSTAR, with this extra data, you're able to get a better, more precise measurement. So not only do you get rid of this ambiguity, but you also get a more precise measurement with NuSTAR. And so what we found for NGC 1365 is the black hole is spinning at least 84% of the maximal speed allowed by relativity. It's a very robust measurement, the first really robust measurement of a black hole spin. At this point, we have about a dozen that we've measured, but most of these spins have been very high. And that kind of fits with, we kind of have 2 ideas of how black holes might grow. One is your little bits of feeding all the time. And then in that case, some should be coming from this direction, some from that direction. And the net result is the black hole shouldn't be spinning that fast. Instead, if you imagine that most of the feeding comes from large accretion events where a big bunch of material falls in on the black hole, that will spin up the black hole almost like an ice skater bringing in their arms. If it's all coming in at once, it just starts spinning up really close as it gets close to the black hole. And so it seems like the fact that we're measuring high spins generally might point to most of the black hole growth is happening in this big accretion events. We're able to start studying the immediate environment about the black holes. And then the big thing is we resolved this 15-year debate in the community. So that was a nice early result from NuSTAR. It was published in Nature. So that's the first big science result from NuSTAR. The second one I want to talk about is supernova explosions. And just to emphasize again, just like black holes, we could give a whole 1 hour or 1 day lecture about supernovae. They're incredibly important things. Basically, the universe started mainly just hydrogen and helium, and then stars burn that hydrogen and helium or fuse it into heavier elements. And everything in our body, like the carbon in our body, the silicon in our computers, the platinum in our jewelry, all was formed in stars and then was spread out into the universe in supernovae. And you might be a little bit confused of how does that happen. As the stars living, like our sun, you have gravity pushing in because the star is very heavy, and then it's burning material that's pushing out. And those balance each other, and we have this largely stable star in the center of our solar system that's burning fuel. In about 5 billion years, the sun will run out of fuel. You'll stop having stuff pushing out, gravity will win out, and the star will collapse. For the biggest stars, that collapse creates an explosion. And one way to think of it is you imagine that here's the heavy inner parts of the star. Here's the lighter atmosphere of the star. Usually this heavier part's being held up by the burning, the regions below it, but as you run out of fuel, nothing's pushing on this, and then gravity will make the heavy inner parts of the star fall in. The lighter atmosphere will follow it, falling back in, but then it will hit the bottom, and the outer parts will bounce off the heavier inner parts. So this is a whoops. Actually, I'm going to do one more just because it's fun. Oh, thanks. Okay. Yeah. So one little problem in that, though, is that theorists trying to create these supernova explosions on their computers over the last 20 years can't get the explosion to happen. You should get that collapse, you should get that bounce back, but in the computer simulations, after about, 100 milliseconds, the bounce back stalls and the star should stop exploding. So there's been this slight embarrassment that the theorists say stars shouldn't actually supernova, and then the observers are saying, well, we see them. And so NuSTAR comes in with a new way of studying the supernovae. There's a slightly complicated slide, but basically, as a star explodes, it creates a lot of very hot titanium. Titanium is an unstable element. It decays, it's a radioactive element. It decays into calcium. And as it decays, it creates high energy photons, X-ray light. You get two photons that are in the NuSTAR band at 68 and 78 kiloelectron volts there. High energy X-ray light that NuSTAR can study. You get a couple other things that are harder to study, like positrons and even higher energy photons. And so the key thing, though, here is that previous studies that people have been doing of supernovae over the last decades have been studying either hot iron or hot magnesium or cold iron. They're measuring different states of material that are dependent on the temperature and the ionization state of that material. NuSTAR comes in, and we're the first ones able to study a radioactive element created in the explosion. And so all the titanium will go through this decay rate, will create those high energy X-ray light. Whereas the iron that had been studied by Chandra, for example, had to be a certain temperature and density of iron to actually see it. It's not nearly as good of a tracer. So this is like DNA evidence, and they were using, fingerprints or something, not nearly as good for trying to understand the supernova. And then the other thing, is that this titanium also gets formed in this region where in some models, the iron falls back with the remnant created by the supernova. And then in other models, people had that titanium gets thrown out. So this titanium line is this very good diagnostic between all the different theoretical models of what the explosion should be like. So this was like kind of a holy grail to be able to study the titanium emission from supernova remnants. And that NuSTAR was the first one really to step up and be able to do it well. Before we launched, there were a range of models of what would happen. I said how the models basically say the explosion should stall. And so there were two different ideas out there of how you might break the stall. Some people said, the star should be spinning quickly. When something's spinning quickly, you might get jets forming. That jet might break the stall. And so there are some models where you might break the stall from the jets, and they predicted that the titanium should make this sort of vertical structure around the remnant of the star. Other people had models where basically you get the explosion would stall, and then they would say, well, maybe there's some extra energy input. They would make up different reasons of how you would get it, but that would break the stall. And those models would predict that you'd get this sort of spherical explosion coming out, and so the titanium should be in a ring. And so basically the theorists were very excited to see whether we would see a line or a ring with NuSTAR. Here's just a more colorful model prior to the NuSTAR launch of what you might see with these jets. Motivating that, if you looked at the silicon magnesium and the lower energy X-rays with Chandra from the Cassiopeia A supernova remnant is a nearby supernova remnant in our galaxy. There's sort of this structure, this long structure, which people would point to and say, oh, it must be the jet that breaks the stall, and that's the physics that's going on. If you looked at the iron, though, from that same remnant, it mainly made a ring, and so people would point to that and say, oh, it's probably mainly the spherically symmetric explosion that's happening. And so basically, people thought we'd either see this or that with NuSTAR. And this is what we ended up seeing with the titanium. We saw these bunches of blue knots, unlike the ring or the line. And completely unexpected by us, completely unexpected by what we put in the proposal when we wanted to do NuSTAR in the early 2000s when we proposed the mission. However, it turned out that in the time that we were so busy building those crazy optics and doing the extendable mast, the theorists had taken a step forward in their modeling and finally gotten to do three-dimensional models, putting in all the physics in a three-dimensional situation. And so actually, even on the third floor of Caltech astronomy, there was models trying to do this three-dimensional version, and this is what their models would show. You get that initial collapse, that explosion out, you get the stall in the explosion at 100 milliseconds, that's just sitting there for a while. And then in the 3D models, you end up starting to get this sloshing that can happen that you didn't see in the two-dimensional or one-dimensional theoretical models. And that basically breaks the stall, almost like I like to think of like when you're blowing a balloon and you're blowing it and it gets stuck and it gets stuck and you keep blowing and then eventually part of it gets expanded out and it basically breaks that and your balloon gets much bigger. And so in their models, they're able to break the stall with a sloshing pattern. And the predictions of their models say that the titanium should basically be in clumps interior to the ring, the symmetric iron ring, and basically fitting very much what NuSTAR had seen. Here's the blue is the NuSTAR titanium in these clumps. The red is the iron shell, and that green is a magnesium, that magnesium linear structure. And so basically, our observations of the titanium fit in exactly with what the theorists were predicting about just in the months before we started making these observations. And so it seems like NuSTAR has solved this question of how do stars explode, which is important for everything around you. So that was another chalked up, good, nice discovery from NuSTAR. And then finally, the most recent one is ultraluminous X-ray sources. And so I mentioned before that, or I showed this picture before of this nearby galaxy, IC342. Most of the X-rays from this galaxy are coming from two knots in the outer parts of the disk of the galaxy. When you look at nearby galaxies, it's rare, but not incredibly rare, that you will see these really, really bright X-ray sources not at the center of the galaxy. The center, we think there's a billion or million solar mass black hole, and if stuff's falling in on it, it creates a lot of X-rays. No surprise if you see a lot of X-rays coming from the center of the galaxy. But these guys in the outskirts have been a bit of a mystery. There's two main ideas that have been going on for them prior to NuSTAR to explain them. One is that maybe they're large black holes, bigger than the sort of black holes that can get formed in supernovae that weigh a couple dozen times as much as the sun. Not as big as the guys in the center, so things weighing 1,000, 10,000 times as much as the sun. And as I said, there's only one of those that's known, but the universe has to be full of them. And so it could be something like that, just feeding at a typical rate. The other idea is maybe they're more like those smaller black holes formed when stars explode, but feeding at incredibly high rates. Rates that can't be stable, we call it super Eddington accretion. In theory, it should be possible, but it can't be a stable scenario. But that was another idea of what might be going on. And then maybe some people thought maybe it's something else, but it was pretty much one of those two is what people were thinking. To put it a little bit in context, here's the range of masses of very compact objects in the universe. At the high end, we see these supermassive black holes at the centers of the galaxies weighing millions to billions of times as much as the sun. We get stellar mass black holes formed when stars explode that weigh a few 10 times as much as the sun. There's this intermediate mass range, which is, there's one object. And then in the lower end, you can get neutron stars. So really big stars, when they explode, leave this black hole remnant. Smaller black holes, smaller stars, when they explode, can leave a neutron star. And a neutron star is basically a big atom. It's just protons and neutrons. It could be on the periodic table. Relatively simple physics tells you it's more neutrons than protons. But something like the sun, if the sun were a neutron star, would be about the size of Pasadena, about 10 kilometers in size. So they're also very extreme, like black holes. But they're made out of things that we understand, protons, neutrons. You have electrons around them. So they're not nearly as weird as the black holes. So where did NuSTAR come in? So we did a big study of the Cigar galaxy, also known as M82. And this is just showing you a couple of pictures of the M82. On the left-hand side, I have a picture with Hubble Space Telescope in visible light, the sort of light that you can see with your eyes. And there's sort of this blue cigar with hydrogen gas coming out in top and bottom. Chandra has also studied this beautiful nearby galaxy and sees a very different picture of this galaxy. This is mainly just beauty shots to show you that when you look in different parts of light, you see very different phenomena. In January 2014, a supernova went off in M82. This is a very nearby galaxy, so this is a bright supernova. And in fact, it was so bright that it was found by college astronomy class at University College London on the rooftop in London doing their star party. And one of the students hey, this isn't in my picture in the book. And so they were the discoverers of this supernova. It was the nearest type 1a supernova, which is one of the subclasses, but a very important subclass of supernova. So it was the nearest 1a in 150 years. So incredibly important source for study. Basically every facility on the planet and in space went and studied it. I think this is a Hubble image of that supernova. NuSTAR jumped on it as well. And we spent about a month studying this supernova because there's all sorts of unique features for studying supernova, like I talked about a minute ago, that NuSTAR has unique access to. I'm not going to talk about the supernova anymore, though. We're still working on that. We have some exciting results, but we're still working on it. The big surprise in this study, though, was that towards the center of the galaxy, there are these ultraluminous X-ray sources in M82. There's astronomers are very good at naming things, so there's M82X1 and M82X1 and X2. Towards the center, there are very bright X-ray sources. M82X1 is actually a candidate for this intermediate mass black hole. Not one that everyone believes, but it's one of the relatively good candidates for something like that. M82X2 wasn't nearly as well studied. The blue light here is the Chandra image of the center of that galaxy. And then the pink is NuSTAR. And so basically, NuSTAR is seeing mainly X-rays coming from M82X2, so from the second ultraluminous X-ray source. And so we spent about a month staring at this galaxy. This is probably the longest observation that NuSTAR has done of a single object, studying the supernova. But as we were analyzing the data, we saw M82X2, so we started looking at that. We did some analysis of it. There's an Italian postdoc, Matteo Baccetti, who was doing some timing analysis. And what he found was that, not for the whole month, but for more than a week of that month, M82X2 was pulsating. It would get brighter and dimmer, brighter and dimmer. This is something that no ultraluminous X-ray source had ever been seen to do. And what we think is happening is that it's a pulsar. It's like a lighthouse. You have black holes can't do this. Only neutron stars can do this because black holes don't have edges and they're weird things and they can't have charge. So only neutron stars can do this. And it's essentially, it's spinning, It's got, as it's spinning, light's coming out of the edges, along the spin axis. And as that light points towards you, it's like a lighthouse where it gets brighter and dimmer, brighter and dimmer, brighter and dimmer. And so M82X1 was pulsating, I think, every 4.2 seconds for about a week of those observations. And immediately, we knew like that meant it's not a black hole. It's not a big black hole. It's not a small black hole. It's a pulsar. And it's way brighter, 200 times brighter than any pulsar anyone has ever seen before. It was a new class of object that hadn't even been dreamt of, a new denizen of the universe that had no idea these things existed. It was brighter, more distant than any pulsar that had ever been seen before. Pulsars, or neutron stars, have a fixed size. They can't get more massive than a certain amount, or else they turn into black holes. So this thing had to be accreting at this extreme super Eddington rate, 200 times essentially the speed limit of how fast you're allowed to accrete. This thing had to be accreting at. Incredible surprise. Theorists confounded, and so I'm an observer. I've been making fun of theorists a couple times tonight. So for this, immediately theorists started writing papers. Some groups said, "Oh, we can explain it. The way you could get this to happen is it's got to have really high magnetic fields, and that's the way you could get this happening." And then another group somewhere else on the planet, "Oh, we can explain it. The only way you can get it is it's got really low magnetic fields, and that's the way it's able to accrete so fast." So, jury's out. We're still trying to understand it. This first one was found in 2014, and then for a long time we're like, is this the only one? Maybe all ultraluminous X-ray sources are pulsars. We don't know. We've been doing timing studies of a bunch, and then it was a bit like waiting for a bus that for 2 years or a year and a half we're waiting to see if there are any more, and then in a single week, our group and a group in Europe simultaneously found 2 more using different data sets. And so now there's 3 of these that are known. And the other ones are in some ways better to study because there isn't another ultraluminous source right next door. So we're in the early days. There's all sorts of studies we're trying to do to both get more information about them, and then theorists are trying to come up with the models to explain them. So summary, NuSTAR is the first focusing hard X-ray satellite or high energy X-ray satellite in orbit. Very low backgrounds, very compact detector, 200 times gain in sensitivity. It's been a really fun ride. We're up to more than 250 published papers out of the NuSTAR mission at this point on a whole range of studies. We've studied the sun, we've studied black holes, big black holes, small black holes, neutron stars. It's been a really exciting ride, and I'm glad to have taken you over on part of it. Here's technical details for the X-ray astronomers. And then as I was digging through the slides, I found from the launch day a picture of Fiona's daughter and then my kids and my wife. And unfortunately, my son's playing piano at a school event that I'm missing tonight, but they'll be at it tomorrow's lecture. And then final, for more information, you can email me, or here's some websites. Happy to take questions. There's a mic over there that they prefer if you go there to ask questions.
Is there any limitation to how long that it can stay up there and work? Is there a fuel or a pointing or anything, a cooling, anything like that?
Yeah, so we, 3 ways we could lose the mission. One is it could break. So far things are going very well. We've lost like 1 pixel in 4 years, so that's going really well. The lasers are slowly degrading, but not at any level that we're worried about. The orbit decays slowly. We drop about 1 kilometer per year. That goes with the solar cycle, but we expect to get at least 10 to 15 more years before the orbit brings us too far down. And then when you get too low, you hit the atmosphere, and then you rapidly crash into the ocean. So that's probably how the mission ends. We could stop getting funding, but hopefully we keep writing good proposals and are able to motivate NASA to keep funding us. Yeah.
Hi, I just had a question. Has NuSTAR at all gathered evidence to kind of support answers for the missing baryon problem?
The missing baryon problem?
Yeah.
Interesting question. I do not think we have done any work on that. That's a lot of the work to try and address that tends to be in the lower energy X-rays or in the higher energy ultraviolet light.
Right, yeah, I saw your range was down to about 3 keV, so I wasn't sure.
Oh, missing baryon or dark matter?
Actually, well, you go with dark matter too. If you've seen any interesting spikes around 3 keV.
So dark matter, again, could be a whole lecture, but a good fraction of the universe is not made out of protons, electrons, neutrons, things we're used to. There's a weird thing called dark matter, and then there's even a weirder thing called dark energy that is actually most of the universe. The stuff we're used to is about 4% of the universe. NuSTAR has done some studies, has 2 papers now out, looking for evidence of dark matter decay in the NuSTAR band. We've set stricter limits than anyone has set before, but haven't detected it. That would have been the whole talk if we had found anything. Yeah. Any other questions or? I think we'll call it. We will be here if anybody wants to come up and ask other questions. But thank you for coming. Thank you for braving the rain, and thank you.